Hello, and thanks for tuning into this talk at the November Great Meeting. My name is Mekhi Dhesi, and I'm a PhD student working with Lior Barak and Adam Pound at the University of Southampton. I'll be talking about modelling black hole binaries in the intermediate mass ratio regime. And this research is done in collaboration with Harold Pfeiffer and Hannes Reuter at the Albert Einstein Institute. Intermediate mass ratio inspirals, or IMRIs for short, are binary systems in which the two bodies have a mass ratio between 1 in 100 and 1 in 1,000. And these IMRIs can be formed in two ways. Either a stellar mass compact object such as a stellar mass black hole or a neutron star can collide with an intermediate mass black hole. And the gravitational waves emitted during such inspirals would have frequencies that should make them detectable with advanced LIGO as well as LISA. And detections of such IMRI gravitational waves should make it possible to explore the dynamics of globular clusters, as this is their likely birthplace. The alternative scenario for an IMRI is the collision of an intermediate mass black hole with a supermassive black hole. And these IMRIs would have gravitational wave frequencies that make them very exciting sources for LISA, and their detections should allow us to explore the dynamics of galactic nuclei. So LISA will be able to measure the early inspiral of IMRIs, yet the merger and ring down will still largely occur in ground-based detectors, and the detection of a source across both space and ground detectors is called a multiband detection. It is understood that radiation from IMRIs will have significant contribution from higher frequency subdominant modes during the later stages. So acquiring source parameters such as frequency and orbital inclination during LISA detection will then facilitate the measurement of these subdominant modes in ground detectors, allowing for accurate overall detection. Research from Janney, Shoemaker and Cutler showed that a merger of a black hole with a medium intermediate mass black hole should be detectable by LISA plus the Einstein telescope with a signal to noise of greater than 100 within 0.4 gigaparsecs, or with a signal to noise of approximately 5 within 1 gigaparsec if using Voyager. Whereas a merger of a larger black hole with a heavy intermediate mass black hole can be detected with LISA plus the Einstein telescope out to 230 megaparsecs. So a reference to this paper is given here should you want more details on detectability ranges. The rates for such IMRI detections are, however, still unclear due to the debated assumptions over possible formation methods, although studies suggest rates of at least a few detections per year from each of the formation channels. So I'll now quickly pull out relevant LIGO detections so far with respect to IMRIs. So here is the familiar masses in the stellar graveyard illustration. And a very important and recent detection was GW 190521, highlighted in the illustration, which had a final mass after merger of 142 solar masses. And this therefore makes it the first clear detection of an intermediate mass black hole, which is tremendously exciting news and strongly validates the need to have waveform templates for IMRIs, which is obvious due to the fact that an intermediate mass black hole is necessary in either of the two IMRI formation mechanisms I mentioned. So another thing I want to highlight here is pre-merger, all but one of the observed black hole pairs have masses on roughly the same order of magnitude. And it was only in LIGO and Virgo's third observing run in August 2019 that we saw the first binary to have a mass ratio even close to 1 to 10, which was GW 190814. So LISA plus future generation ground-based detectors will dramatically improve the sensitivity for low-frequency gravitational wave signals. And because the frequency of the emitted waves at merger scales inversely with total mass, this will allow us to detect signals from ever heavier binary systems, including intermediate and supermassive black holes, thus opening up the potential for a new era of observations from unequal mass binaries. Now, successful detections and parameter estimation of IMRIs will require the construction of accurate waveform templates for data filtering. The creation of waveform templates for binaries depends crucially on the mass ratio between the two bodies. So when the mass ratio is small, on the scale of 1 to 1 to 1 to 10, numerical simulations can successfully evolve the system through in-spiral merger and ring down. However, as the mass ratio of the two bodies increases, the computational cost of the simulation also dramatically increases. The computational runtime in numerical relativity scales as the large mass ratio squared. So due to the disparate length scales and time scales present in IMRIs, computational efficiency is lost and the system cannot be feasibly numerically evolved. When the mass ratio is large, say 1 to 10 to the 4 and higher, then black hole perturbation theory works well, and the smaller body is effectively treated as a point particle on the scale of the spacetime. However, this expansion is presently only available at leading order in the small mass ratio, and such a perturbative treatment is likely inaccurate at intermediate mass ratios. Finally, in systems with large orbital separation, we can use post-Newtonian or post-Minkowskian methods for modelling. However, these approximations break down in the strong field regime and hence cannot work for the vast majority of orbits during any binaries in spiral. There has been progress for extending modelling techniques at either end of this mass ratio scale to capture IMRIs. From the side of numerical relativity, there has been very impressive work done on modelling mass ratios up to 1 to 100, using state-of-the-art adaptive mesh refinement techniques. Lusto and Healy at the Rochester Institute of Technology in June of this year published a paper where a 1 to 128 mass ratio binary was evolved through a record 13 orbits before merger. And the plot here shows their obtained waveforms from successively higher mass ratios, from 1 to 15 up to 1 to 128 in the light blue. However, full waveform templates for IMRIs will require the modelling of hundreds of orbits to accurately model the system. From the side of black hole perturbation theory, Vanderment and Pfeiffer looked at the first order post-adiabatic expansion and concluded that this perturbative approach could likely bridge the mass ratio gap from binaries with extreme ratios down to the comparable mass ratios covered by numerical relativity. And this is depicted here in their quantitative adaptation of the earlier plot by Barak and Pound. However, the first order post-adiabatic expansion requires the small mass ratio in expansion in its entirety to first order and also parts of the second order calculation. And the computation of second order effects in black hole perturbation theory is extremely challenging. And although steady progress is being made, it is unclear how long it will be before waveforms are readily available for generic orbits around Kerr black holes. Furthermore, these results by Vanderment and Pfeiffer on the first order post-adiabatic expansion apply only to simple systems of black hole binaries without spin or orbital eccentricity. So to complement the current efforts in attempting to bridge the modelling gap, our method hopes to hit the problem from a different angle. Our hybrid approach proposes to tackle the problem through a combination of black hole perturbation and numerical relativistic techniques. The overall idea is to construct a sufficiently accurate solution of the full Einstein field equations for the binary spacetime by matching an approximate analytical solution near the small object to a fully nonlinear numerical solution everywhere else in the spacetime. So a region around the small object is excised from the numerics, like a bubble around the body, and inside this region we place an approximate analytical solution. And the effect of this will be to relieve the scale disparity that blocks the efficiency of the numerical evolution and reduces the volume of the spacetime needing to be highly numerically resolved. The approximate analytical solution around the smaller body will be formed from a tidally perturbed black hole metric. So put simply, the otherwise Schwarzschild metric of the smaller body will incur perturbations in the form of tidal moments due to the gravitational presence of the larger black hole. The final model will require a 3+1 dimensional evolution for numerical relativity. However, we began by analysing a scalar field toy model. And this is the simplest possible model that captures enough physics to be relevant without having to worry about the full Einstein field equations and their nonlinearity. So we do this by replacing the smaller black hole with a scalar point charge on a circular equatorial orbit around the Schwarzschild black hole in order to test the ideas of the matching procedure. We therefore begin by solving the scalar wave equation in Schwarzschild spacetime with a delta point source. So using spherical harmonic mode decompositions of the field and the source, the problem can then be reduced from a 3+1 dimensional setup to a 1+1 dimensional setup. And in this case, the approximate analytical solution is the retarded field, the appropriate physical solution to the scalar wave equation. We have developed two schemes for evolving this 1+1 dimensional scalar toy model. A model that uses characteristic slicing and finite difference methods to numerically evolve the field, and one that uses Cauchy slicing and spectral methods. And the second is more amenable to the gravity model, giving the numerical evolution there will be carried out by the spectral Einstein code at the Albert Einstein Institute. So in both approaches, the field is numerically evolved along a time slice up to the excision region, or the world tube as we also call it, and numerically determined values surrounding the excision region are then used to solve for unknowns in the approximate analytical solution through a fitting procedure, and this fitting procedure is the matching. In the gravity case, these unknowns will be tidal multipole moments within the tidally perturbed black hole metric, whilst in the scalar toy model case, it is coefficients of the expansion of the regular field within the retarded field. So the fitted analytical solution then feeds back into the numerical determination of field values outside the world tube at the next time slice, be that through a finite difference algorithm in the finite difference method, or through boundary conditions at the excision surface in the spectral method, and information then propagates out from the matching surface. So here are some results from the finite difference scheme for a static mode of the field, so an L equals 2, M equals 0 mode. And what is plotted here is the field taken at a slice of late constant time against the tortoise coordinate r star. So in the toy model, we are working with the scalar wave equation in short shell spacetime with a point source. And this equation has a closed form solution for static modes. So at this stage in our research, we actually have the luxury of being able to test the accuracy of our hybrid matching model by comparing its results to the true static solution. There are two main things we want to test to see if the model is behaving as expected. So the bottom two plots are showing a zoom in of this central region around the world tube where we can see comparisons more clearly. And vertical lines are showing the position of the world tube boundaries. So the plot on the bottom right, on the bottom left, sorry, we are examining the effect of the resolution in our numerical evolution. So the static solution is plotted here in black, and then there are then 3 runs of our model plotted in dashed lines with differing grid size, given by the value of h. And you can see that with decreasing grid size, i.e. increasing resolution, our model's results are converging towards the true static solution. So this is in line with our expectations, and we can quantify this rate with convergence tests. The plot on the bottom right instead shows results from fixing the resolution, but decreasing the width of the world tube, or decreasing the size of the excision region, given by the value of delta. And we again see convergence towards the static solution, which is exactly what we would expect given that the static solution is for a point source. We have also seen that with an increasingly accurate approximate interior solution, the rate of convergence of the solution with world tube size is faster. Although non-static modes are not plotted here, they are also in line with our expectations. They are numerically stable, and they show the same behavior as the static modes. Namely, they have the same convergence rates with respect to resolution and with respect to world tube size. And now here are some results from the spectral method. Again, for a static mode of the field, an L equals 2, M equals 0 mode. And what is plotted is the field at a slice of late constant time against the tortoise coordinate r star. And 4 shots show the results from our model's evolution in time. The exact analytical solution again is here in solid black, and our model's results are plotted now in dashed blue. In this run, we have simply used 2 spectral elements, one either side of the excision region, and 30 grid points per element, and a Gaussian wave packet for the initial data. The spectral method due to its use of Cauchy slicing as opposed to characteristic slicing, requires the implementation of appropriate boundary conditions, both at the edges of the numerical domain and at the world tube boundaries. So these had to be formulated appropriately. We fit the unknowns in our approximate analytical solution by using values of the field and its derivative at both sides of the world tube. And we see excellent agreement between the two results, so the analytical solution and our model, by the last shot here, which occurred at a time of only 175 steps in M. We also see the same overall behavior as in the finite difference scheme model. So when looking at a static mode and increasing the resolution of the numerical simulation, either by increasing the number of grid points or the number of spectral elements, we attain better agreement with the exact analytical solution. And in this scheme, the results converge exponentially, which is as expected when using spectral methods. And when we decrease the world tube size, we also obtain better agreement with the analytical solution. And we find faster convergence rates when we increase the order of the interior approximate analytical solution. So the aim of the excision method and the matching procedure is to reach a sufficiently high order in the analytical solution to relieve the disparity of length scales in the problem, so to relieve the disparity of length scales in the numerical evolution, whilst balancing the number of unknowns needing to be fitted for. And all this can be trialed with our toy models. We are now transitioning to a 3+1 dimensional scalar model, and then the inclusion of radiation or back reaction to model the full inspiral and merger of the system. And it's at this stage that we'll really be able to start probing the numerical efficiency and savings of the excision method. As up until now, we have really focused our experimentation on setting up the architecture of the world tube and testing the matching methods. We will then move to the gravity model, where the numerical evolution will be carried out by the NR group led by Harold Pfeiffer at the Albert Einstein Institute using the SPEC code. And for the analytical solution here, we will be using the tidally perturbed black hole metric. Although metrics of tidally perturbed Schwarzschild black holes already exist in the literature, we will need to use a coordinate transformation in order to put them into coordinates that will mesh well with those used in the numerics, those used in SPEC. Our long-term aims will then be to extend the model to Kerr spacetime with the inclusion of spin to represent realistic astrophysical scenarios for black hole IMRIs. And then to the case where the smaller body is not a black hole, but is a neutron star, therefore including internal structure and using a tidally perturbed neutron star metric within the excision region to cover this case as well. So thank you very much for listening, and please get in touch if you have any questions.